we propose GraviCap, a new approach for joint markerless 3D human motion capture and estimation of free-flight object trajectories from a single monocular RGB video. In contrast to existing monocular methods, we can recover focal length, object trajectories, as well as human bone lengths in meters, along with the ground plane's orientation, thanks to the awareness of gravity. The proposed formulation with human-object interaction constraints ensure the geometric consistency of the 3D reconstructions and improved physical plausibility of human poses compared to the unconstrained case. PhysCap improves initial kinetic human poses with physics-based pose optimizer, yet it does not reach the accuracy of the proposed GraviCap in global position estimation. Our approach differs from these methods in that we assume scenes in which humans interact with objects and bring those to a free flight. During the free flight, the object's trajectory is parabolic in the 3D space and can be faithfully estimated relying on Newton's law of universal gravitation, assuming no other forces acting on the object, such as air resistance. Such motion is entirely described by the initial position, initial velocity, and the gravity vector, which our method estimates together with the human poses. Our scenes of interest abundantly occur in real life, for instance, while playing games or practicing sports. GraviCap accepts monocular video as input, which is used for 2D object tracking, 2D human pose estimation, and initial kinematic 3D pose regression. Those are then fed to the primary optimization objective, which is jointly optimized for human poses, initial object position, initial object velocity, the focal length of the camera, and direction of the gravity vector. Our objective function includes 7 terms. The term E_B recovers 3D object coordinates with respect to the camera, which are parameterized by the initial object position, initial velocity, focal length, and gravity vector. The term E_P recovers subject's poses in 3D, including per-frame corrections for the global root translation, per-sequence bone lengths of the subject, and the scaling factor that converts the up-to-scale distance estimates to absolute units, in other words, meters. This term also co-influences the focal length recovery. F_C expresses human object localization constraints, which improves the physical plausibility of the human poses. This term localizes the subject with respect to the 3D object's trajectory, and works well because the trajectory estimation from 2D observations is a highly over-constrained subproblem. E_M, or the human object localization, is expressed as a sum of joints to object distances which are constrained to match their 2D reprojections. Next, E_S expresses the assumption that human bodies are symmetric, and E_BL penalizes large deviations from average human bone lengths. Finally, E_CO is used in the case of multiple free flight episodes in the same sequences. It ensures that the next free flight starts close to the final grasp or bounce position of the previous free flight. All terms are jointly optimized with Levenberg-Marquardt for all unknowns over the entire video. The entire optimization takes place between 3 seconds for a scene with a single free flight episode to a few minutes with 12 such episodes. At the end of optimization, we obtain the initial object's position and velocity, focal length, the direction of the gravity vector, bone lengths, corrective translations, and final object trajectories, and global 3D human poses, all in metric units. To evaluate our method and establish a benchmark for the new problem, we record a dataset with 4 subjects and 9 sequences. For each sequence, we provide 3 synchronized videos of the scene, ground truth intrinsic and extrinsic camera parameters, ground truth human poses, and ground truth object trajectories for each view. Each sequence contains several multi-episodes, with a total of 63 multi-episodes and 252 episodes in the dataset. We observe significant improvements in global root translation estimation over VNect and PhysCap. Note that MotionNet was not able to produce reasonable estimates on the new sequences. In bone length estimation, GraviCap outperforms VNect, which assumes average bone lengths of a predefined skeleton, in 7 cases out of 8. Note that only our method additionally estimates focal length and floor normal, whereas other methods either require these inputs or are agnostic to those. Only our method can estimate 3D objects' trajectories. 3D MPJPE, considered in isolation, hides artifacts in the reconstructed motions such as jitters. Smoothness in motions is thus an important criterion of physical plausibility. Our algorithm outperforms VNect and Vibe on this metric, thanks to mutual direction and more stable bone length estimation. Note that PhysCap makes a much stronger assumption, a known body mass distribution, unlike our method. The qualitative results of our method on several videos in the wild. Note how smooth the reconstructed human poses are. Also, our estimates of the ground plane seem to agree with the observed floor orientation very well. Thank you for watching.